Now in this lesson we are going to study about comparing two population mean values, or for short, comparing two population means. And so before we really proceed, it is highly recommended that anyone viewing this video lesson here must view the lesson here after a successful understanding of testing a hypothesis for population mean, as well as how to construct the general understanding of how to construct a confidence interval to estimate population mean. So if you have arrived at this video lesson and without the understanding of how to test a hypothesis on population mean, then I highly recommend that either you can find my other videos on testing a hypothesis for population mean, or find it elsewhere to understand before you can understand the concept of being highlighted here. Let's take a look at a few highlighted concepts, a few highlighted key points in this lesson before we get started into doing a real problem. And so the idea about comparing two population means is that, to keep it simple, let's say starting out with a mean value that we the scientist, anyone, is studying, then let's say mu here, I'm going to bring up a scenario. Let's say our mean value here is the population mean. It's the mean age to have high blood pressure. All right, so think about or imagine that this is the mean age, a population mean value that a lot of medical doctors are interested in, or a lot of health scientists are interested in, because once we understand this mean age right here, we can use that mean age to have high blood pressure as a reference to find a way to medically improve the mean age to have high blood pressure, because high blood pressure is a condition that eventually anyone at a certain age is going to have high blood pressure. It's a sign when your body is getting old and blood vessels are not working as well as those days you are young anymore. And so that's what this mean value is for. It's the mean age for anyone. So anyone has a certain reach to a certain age when your body starts developing high blood pressure. And so here in this study, we're looking at the mean age to have high blood pressure. So this is only one example that I'm bringing up, one quick little scenario that I'm bringing up right here. So right now, as I'm looking at that, and it's just simply, it's a population. It's one population mean value that we're looking into the mean age for the entire population of people. So now let me bring up into a further situation. We're still looking at the mean age here. This is the general mean age, population mean age to have high blood pressure. But now let's look into this quick little scenario right here. And the mean age to have high blood pressure, I actually brought it up from this data that I have obtained. Now, I am not saying that the data I'm showing on screen right here is any longer valid, is any longer solid, but we can still use that as a demonstration of what we're studying here. But so, and I apologize for the very sketchy description of the data here. But so basically, for the age for high blood pressure here with a colon, it really means I'm studying the mean age for high blood pressure. But so the idea of comparing two population means now is that you can see now after this line right here, I'm starting to get straight into the two descriptions of the two separate samples. So the idea now is that for the same age for high blood pressure, but I am now studying to find out if there is going to be any difference between that mean age of high blood pressure, but we're looking for that in the among the male patients, or we're looking at among the female patients. So now we don't need to worry about all the numbers provided here yet, but let's swing back on my writing board here. So the idea now is that apparently the same mean age, but we can look for that in two separate populations. So quickly from the description that we have seen on the computer screen, then in the man population, we can find that mean age. We can look for the same mean age to have high blood pressure in two separate populations. And so that mean age, that general mean age, population mean age to have high blood pressure also exists in the woman population. And that's the idea, or at least the beginning idea of what it means by comparing two population means. Because once we have isolated the same mean age to have high blood pressure here into two separate populations, then we can start asking ourselves the questions such as, is the mean age to have high blood pressure in the man population higher than that in the woman population, or the other way around? And so that's what it now truly means by comparing two population means. And so now, to successfully move on much further, I have to also address a few key points here for the rest of our study here with comparing two population means here. So it is extremely beneficial and quite crucial that we must name our two separate populations here with two numerical labels. And so the numerical labels come out as our own choice. And let me directly demonstrate that on screen right now. So as a choice, simply as a choice, doesn't mean I favor any side here better than the other side, but simply the numerical labels I'm about to give here are just labels to keep things easy to reference among our two populations here. So let's now call the man population, population 1. And that's the reason why I write it in red pen right there, in red ink, because I want anyone viewing this video to understand how important this numerical label is. And as I said, I chose man here to be the population 1, simply it's just a choice. Maybe because back on the computer screen, again, the male patient was introduced first. That's probably just the order of how the data is being introduced, and I made that choice. But anyone viewing out there, if you happen to do the same work independently with me, you can also have your own choice. You can label this man population or the male population to be the population 2. But then on the other hand, that means the numerical label we can assign for the woman population is to be regarded as population 2. So first important understanding is that instead of keep referring to these two populations as man population and woman population, we now have a better name and easier to keep track of. This is population 1 and this is population 2. And so we can call this population 1 and this is population 2. And being 1 or 2, again, just came straight out as a choice at first. But now a further intention of mine is that once we have made our choice, or anyone has made your choice here for giving a numerical label on each of these populations, then we have to stay in that order, in that particular choice of yours. So what it means now as a further impact is that this mean age to have high blood pressure, and by the way, allow me to start using shorthand writing for high blood pressure. How about HBP here? There's a short handwriting for high blood pressure. So that mean age to have HBP, now if we're looking for that in population 1, then it becomes a mu 1. That's what I keep trying to emphasize about how important we are trying to give numerical labels. So this could have been label 2, then that means mu here gotta be mu 2. This could have been population 1 with label 1, then the mu there, once we're isolating that into this population, we gotta call it mu 1. But now in this particular convention, in this particular decision that I have made, then I call my man population here being population 1. So that mean age to have high blood pressure but now within the man population, it's called mu1. And so similarly, that same mean value, mean age to have high blood pressure, to have high HBP in a woman population, now regarded as population 2. We call that mu right there, mu2. And so now, comparing two population means, in this case here, we're comparing in the sense that we are studying the difference. So I'm now going to define the difference D here is defined as permanently mu1 minus mu2. So we quantify, so comparing a lot comparing in common daily language means we want to find out whether mu1 is greater than mu2, or mu1 is less than mu2, or mu1 is equal to mu2. But now in a strict mathematical point of view, then we quantified our comparison by looking at that in terms of a difference. And so again, what I'm trying to say now is that comparing two population means we first define the difference between the two population means, and we always stays in that order: the value, the parameter that came out from population 1 minus the parameter from population 2. And then so comparing just means, is the difference here a positive difference, or is the difference here a negative difference, less than 0 quantity? So positive difference means mu1 is greater than mu2 in the way how we label our two populations. D being less than 0, or the difference being less than 0 here means mu1 is less than mu2 in the way how we are defining our, in the way how we are given the two numerical labels to our two populations here. And same way, the difference can also equal 0. We want to find out whether our difference is positive, our difference is negative, or our difference is equal to 0. And again, the difference equals 0 here means mu1 is equal to mu2 in the way how we already assigned the numerical labels to our two populations. All right, and now that we have understood what it means by comparing two population means here, we comparing two population means by simply looking at the difference between the two population means to see whether it's a positive difference or a negative difference or an equal 0 difference. And again, now I set aside this formula here and put that in red box now, and emphasize that it's always, anytime we're setting up a difference between two population means, we must always go with the one that came out from population 1 minus the same parameter that came out from population 2 here. And that's a permanent definition of our D here. This D is the difference in two population means. So now, in that way, how I have already defined or given the labeling, the numerical labeling for the two separate populations here to keep track and making it easier to organize. Then so now the further impact we have already seen is that the same mean value here, but if we're now studying that in the population 1 within population 1, or isolated that in population 1, then we call that it's mu1, and the same way this is called mu2. So now having two separate populations in hand here, we can independently collect samples. So this population 1, from this population 1 we can collect our own samples, and from this population 2 we can also collect our own samples. And so one more time, once again, let's have a look at the description of the data given in on our computer screen here. And so now, as I have mentioned earlier, here we simply having two descriptions of two separate samples. So one sample here we have is a sample of male patients. So apparently this was a sample that is from the man population. And so let's read a little further. So in this sample, it's a sample size of 400. That's what it says right here, quite obvious, 400 male patients. So it's a sample that we selected from population 1. And So now clearly this is a sample mean here. So in this sample we found the mean in this sample that those male patients there reach to high blood pressure is a 42.5. So this is a sample mean in this sample from population 1. And as well as we have a given sample standard deviation from this sample. And so putting that into the right place, we pick that sample from population 1. So that means I have to now call that the sample size that I used there is, I have to call the N1. And N1 here is 400. And the sample mean that we chose from this sample that we've had, and everything I'm looking at right now is selected from population 1, is to be placed under population 1 or from population 1. So it must stay in this left-hand side column of my growing table for now. And so the sample mean that we've had there must receive the same numerical label, X bar 1. So the subscript I'm using here is not to indicate that it's the first sample or the second sample, but this is the sample that came out, the sample value, the statistic that came out from population 1. And so from the screen we've seen that we have given a sample mean, our sample mean from population 1 is 42.5. The sample standard deviation is a lowercase s, but this time it came out from population 1. We call that S1, lowercase s1. And the value we had given here was 3. And again, as I said earlier, this data I'm looking at here is not necessarily accurate, but it's still useful as a demonstration of what we are studying. At least it demonstrates the idea of what we can do, even if I'm not very sure about whether my data are still any further correct or accurate. And so the same way here on the computer screen. Now if we're looking at the female patients, so it makes sense that this sample and every information regarding this sample must be placed on the right hand side column on our table here, because that sample came out from the woman population. And in here, in my selection of numerical label, it's population 2 with the label 2, numerical label 2. And so quickly on the computer screen, we also collect 400 female patients. And so that sample size we have, and right from that, somebody calculated the sample mean for us being 51.2. So what it says here is that in this sample of 400 female patients, then we found that their mean age to reach high blood pressure was at 51.2 years old, and the standard deviation there is 4.5. So all information here, they're all sampling information. They're all sampling statistics. And now on my writing board, so now I know that the sample size I use, the sample size that I picked from this population 2, now symbolically N2. So 1 or 2 again is not because this is the first sample and this is the second sample. Nope, it's not that. 1 or 2 is only to reflect where our sample came out from. So that's the subscript 2 right here. It's indicating that this is the sample size of all samples we use in population 2. And so N2 here was given to be 400. The sample mean we have seen back on the computer screen, X bar, now must be given the numerical label as a subscript, X bar 2, and the value there is 51.2. And of course, the sample standard deviation, the standard deviation that stays only in the sample we picked from population 2, we call that S2, lowercase s2. And this is given to be 4.5 according to our data. And that's the importance of how we chose from the beginning. That's the importance about our decision on giving giving numerical label here. And I said in the beginning it was a choice, and there's no hard rule about how to choose. But what's important is once we chose these numerical labels, then all of these values from the corresponding population must be given the exact same subscript indicating where they came from. So population 1 gives the subscript 1. Population 2, all of these value gets the subscript 2. And so now I have to clarify another further thing right here. So as I said earlier, when I'm saying x bar 1 and x bar 2, it does not mean this is the first sample and this is the second sample. What I'm saying is, in our about picking samples, we can still pick many different samples from population 1. So this could be, if this is our first sample from population 1, we can call that x bar 1, and we can give it a superscript 1 to indicate that this is first samples. So now let's look about all the samples here. So the superscript really is to indicate first samples from the same population here. So x bar 1 first sample could be the 42.5 that we've had here. And then after this one, recall from the idea of picking samples from a population. This is one population. So after this sample, we can pick another one. So there will surely exist an x bar 1 again, because these are all from population 1. But second sample, that's if we have to be in that situation, if we are planning to pick multiple samples from one population, then we can start using superscript to indicate. And since I didn't have any second sample after this one from population 1, then I'm just leaving it as a blank, or just leaving it as dots there. And we can further have x bar 1 again. So the subscript in this study of ours is permanently indicating that all of our samples currently are from population 1. But superscript 1, 2, and 3, they are indicating different samples from the same population. And now this N1 right here, again, the subscript is to indicate that the sample size we use here is the sample size that's decided in population 1. And so that means if we are using, the first sample was already 400, the second sample from population 1 must be the same sample size as the rule for picking samples. And so that's what N1 equal 400 means. If we pick other samples from the same population 1, then all of these must come out at the same sample size. So now, same way, if we're now looking over to the population 2 here, then again, we have already used the subscript to indicate where our sample came from, which population our sample came from. So sample mean x bar 2 right here means it's a sample that came out from population 2. It's only indicating where we selected that from. But if this is first sample, and let's say maybe 51.2 is our first sample from population 2, then if this is our first sample, we can give that a superscript to indicate first sample. And then again, the same idea how we pick samples. Once we can pick up one sample, we can pick up another one. But this other one that we're about to pick up is again from the same population 2. So we must call that with the subscript. So here x bar subscript 2. But now being the second sample, we can call that, we can use a superscript. So superscript in this case, if we have to, again, I'm only saying if we have to pick more than one samples from each population, then we give superscripts to indicate the order of our samples here from the same population. And so since I didn't pick a second sample in this study here, and I didn't even have that given information, I'll just leave it blank or dots right here. And again, if we are picking a third sample, but from population 2 again, then I have to call that symbolically x bar subscript 2. X bar is for the sample mean. Subscript 2 is to indicate it came out from population 2. And third sample is indicated as a superscript. And so since we didn't have any of those, I can leave it blank, but realize that any of these exist. It's just we didn't need to find all of those. And so again, N2 equals 400 here just simply means that doesn't matter how many samples we want to pick or we want to select from population 2, but all of these must agree. All of these samples must agree to be on the same sample size. We call sample size N2 equals 400. So if this first sample here was at sample size 400, if we pick another one, a second sample from population 2, then it has to also be 400. Okay, and so N1 and N2 is more about what sample size we decide to pick from each population correspondingly. But now the important thing I need to address before we are heading any further. So now if you're well understanding what N1 and N2 is, now I can clearly tell you N1 and N2 do not always have to equal, need not. Now this not equal here, I don't mean always have to be different, but it means needs not. Okay, N1 and N2 need not equal. Okay, so here it happens to be that we decided to have equals, to pick equal sample sizes from two separate populations, but in other examples that I may bring up later on, sometimes you can see that the sample from population 1 is decided, any sample from population 1 could be different from the sample we picked from population 2. And so when we're doing this right here, N1 and N2 need not equal. And so in this style, in this way how we allowed different sample sizes from different populations to be different like this, then this kind of problem right here we refer to as, and I will explain more about the terminologies here, but the kind of samples we are using here are, first of all, they are independent samples. There are other kind of problem where we're working with dependent sample, but that's not within our class to learn right here. So this video lesson is to aim as treating these two samples or independent samples as in they came from independent populations. So these are independent samples. And so independent samples are allowed to have different sample size. And these two are independent samples, and further they are unmatched. So find my other videos at some point to understand what matched samples are, but these are unmatched. And that's why they are allowed to have the different sample size. Unmatched or unpaired. And so at this point, anyone again viewing this video can realize, and I hope I trigger that realization of yours, that from each population we can pick as many samples as we want. And all samples from the same population must agree to one decided sample size from that population. And sample size from two separate populations do not need to equal. But now fundamentally here on each of these columns, as far as the samples, we can still have many more samples. So now let me do this quick sketch right here. Let's say I'm gonna pick a pair. I'm gonna pair up, and pairing up, I don't mean to be the opposite of unpaired samples here. What I mean is any two samples, each from a separate population. Let's say our sample 1 from population 1 and sample 2 from population 2. This arrow, this line connecting here just means I can take sample 1 minus sample 2. So that's right there indicating this pair can be used to make a difference in values. And so I can go sample 1 from population 1 minus sample 2 from population 2. that gives me a difference in the sample. And so now notice, I am not using the lowercase letter d, but here it's a lowercase letter d with a bar on top. So d bar here, just pick any two random samples from two separate populations and subtract them. Again, pay attention to the order of the subtraction right here. The value that came out from population 1 comes first before the subtraction sign. And then the value that came out from population 2 comes after the subtraction sign. And so we can also have another difference. We can do like this. That means we can have another difference, being sample mean 1 from population 1 minus sample mean 1 from population 2. This is also a value for our d bar right here. And so we can mix and match a lot of these to find a difference, any difference. And that's what now the arrows connecting any member from one side to another member of another side right there. And that's what these connecting arrows are for. So now we realize that we can have infinitely many differences in sample mean values from two different populations. And so generally, let's now define a d bar here, means to equal an x bar 1, no superscript, minus an x bar 2. Okay. And now, importantly, x bar 1 is not this particular value, is not that particular value. It just means x bar 1 is a sample mean, any sample mean, a sample mean from population 1, and allow me to use shorthand writing in parentheses 1. So x bar 1 just simply means we pick any sample mean from population 1. That's what x bar 1 is for. And so similarly, x bar 2 in our quick definition there that I put in a box, x bar 2 just means a sample or any sample mean from population 2. And that's what this is. That's what, so we just simply pick a sample or any sample mean from population 1 and subtract or take the difference with any sample mean from population 2. What we have there is a value that we call d bar. And so now in that way, how I have defined my d bar over here, then let's compare and understand the true difference in meaning of the two values here, because fundamentally we've learned earlier that there's a d and now there's a d bar right here. And it's always in the convention, again, the convention here is that we always take values from population 1, and that's what subscript 1 is for. We're always going to take value from population 1 minus that similar value from population 2. But now in a way how I define here, and particularly pay attention to this explanation about x bar 1 and x bar 2 in this formula, in this definition of my d bar, then so now I can say that, now I can tell to any viewer, and I want to leave that for viewer to take a moment. You can pause the video to understand why I'm saying so. But this d right here, once we can find it, it has only one, this d value has only one unique value. That's what I can guarantee about this value for d. Once we know it, once we can calculate it, it will only have one unique value. Take a moment to understand why. And then the same way here, but this d bar in the way how we define, we can just pick any sample mean from population 1 and subtract any sample mean from population 2. And so in the way how I drew my chart here earlier, then now I can guarantee that we have an unlimited number of values for this variable. So this is more like a variable now, whereas this is one unique value if we know it. So that's the major difference between D and D bar over here. And so now upon realizing that our D bar here being the difference between a value, a sample mean value from population 1 and a sample mean value from population 2 has unlimited number of values as we have already understood, then we can now clearly agree that D bar is a random variable, and as a matter of fact, a continuous random variable. Random variable. So, as I keep saying earlier, anyone viewing this video lesson here must view this after understanding about how to test a hypothesis and how to construct confidence interval. So that consequently means further that our video here must also be viewed after anyone already had a solid understanding in terms of what a continuous random variable is, and as far as and as well as a sampling distribution. And so further, you can see that D bar represents this random variable right here represents a sampling distribution. A sampling distribution of differences in sample means, and of course from two separate populations. So these are the two highlighted key points as well to be addressed. And so now in that way, without a formal introduction, central limit theorem that anyone viewing this video has already been comfortable with has a version that I so-call extended central limit theorem, extended version. So here I'm going to quickly introduce the extended central limit theorem. So we're going to briefly mention that. So based on what we understand just earlier, then since D bar here is a random variable that represents a sampling distribution of differences in sample means, then we can extend the central limit theorem. The extended central limit theorem states that the center of this random variable, or the center of this sampling distribution, is regarded as the population mean of all D bars. Once again, because we can have infinitely, or we have unlimited number of values, so we can average out, and that's the center. So this mu D bar right here is the center on the sampling distribution of differences in sample means. And so the extended central limit theorem says this value, doesn't matter how you calculate, will turn out exactly equal D. And so recall for yourself that D equals to mu1 minus mu2 for whichever we call mu1 and whichever we call mu2, but it's strictly mu1 minus mu2. Average spread namely sigma d bar here is found, and we formally call this the standard deviation of all sampling differences. If we know the two population standard deviations, sigma 1 and sigma 2, and now we have a math problem. Sigma 1 square over n1 plus sigma 2 square over n2, and put that expression inside the square root. This expression here, according to the extended central limit theorem, is what's giving us the standard deviation value, the population standard deviation value of all sampling differences in the sample means out there. If for any reason that we know the population standard deviation from population 1 and the population standard deviation from population 2, and that's again that's what explains for the subscripts 1 and 2 and 1 and 2. But now, since we usually do not know, and it's a very challenging and it's a lot of difficulty to know the actual population standard deviation 1 and population standard deviation 2, the two separate population standard deviations from population 1 and 2 here are usually hard to find, very difficult to find right there. And so we usually approximate this average spread by a what's so-called standard error. SE, which is given by the formula S1, the sample standard deviation right from your sample from population 1, square over n1, the sample size that we use on population 1, plus sample standard deviation from your sample from population 2, square plus, divided by n2, and we take that inside the square root. So this is called a standard error that's usually used as a way to substitute, and it's a close enough approximate of our sigma d bar right here. But now for students in my class in particular, I also usually refer this to students in my class, even though the public viewers do not necessarily have to follow this. But I usually refer this standard error to my own students as combined standard error, and I use a subscript C right here. So SEC is what I introduce with my students, which is the same as the usual standard error that approximates sigma d bar. But for my own class with my own students, I usually refer to this as a combined standard error. It's not really anything that we're combining in two samples. Don't get me wrong on that, but it's just simply because a lot of time the formula here, I'm just trying to trigger for my students to make it easier for students to remember that it combines, this standard error here combines somehow in this way of how this formula is set up. It's combined the two sample standard deviations together, and each one of these is playing part in our usual standard error as we know when it was still in one population. And so I step a little bit forward and call this, it's a combined standard error, even though a majority of teachers and professors out there just refer to this as simply the standard error. So as a clarification, SEC in my class is just the same as standard error out there, same formula. And usually at our beginner stats course level here, then this random variable d bar, notice as being a random variable, but here in this case I don't even have to use a capital letter, but now we already have an understanding that this is a random variable. And so according to the extended central limit theorem, and usually, as I said again, for the beginner level in statistics, then we don't have to see too much detailed proof or anything like that. But usually our random variable d bar here is, or at least approximately, on a normal distribution, where center is the mu d bar and It's sigma d bar for average spread. So we don't even have to worry for our beginning level here. We don't even have to worry any particular condition, because usually our sample sizes are good enough for us to assume that we have a normality or a normal distribution on our sampling distribution of all the sampling differences. And that's a general brief understanding of the extended central limit theorem.